All right, welcome. Today we are opening up your very first electronics toolkit, and we're starting with two of the most essential, must-have circuits you'll ever learn, voltage and current dividers. Let's dive right in. So let's imagine a super common situation. You got a standard 9-volt battery. We've all seen them. But the little component you want to power, maybe it's a specific LED or a sensor, well, it can't handle 9 volts. It needs something lower, like 5 volts, maybe even 3. So what do? Do you have to go find a whole new power supply? No way. There's a much, much cleverer solution. And that right there brings us to tool number 1 in our new kit, the voltage divider. This is your absolute go-to for taking a big voltage and just dialing it down to the exact smaller voltage you need. And the secret? It's all about a simple, clever arrangement of resistors in series. So here it is. This is the basic layout. You've got your voltage source on the left, that's our battery. And then, here's the important part. You have two resistors, R1 and R2, connected one right after the other. That's literally what in series means. They're connected in a single line. So what is a voltage divider, really? Well, it's this beautifully simple circuit that just uses those series resistors to turn a big voltage into a smaller, more useful one. You can think of it like a tap for electrical pressure. It lets you draw off just the right amount you need. I mean, this is the basic idea behind things like a volume knob or a light dimmer. And of course, there's a little bit of math that makes all the magic happen. To figure out our new lower voltage, we'll call it V2, you just take your starting voltage, Vs, and you multiply it by a ratio. And that ratio is just R2 divided by the total resistance of R1 plus R2. The cool part is, by picking the right resistors, you get total control over that output voltage. And this, right here, this is the golden rule you need to remember. Voltage across series resistors divides proportional to resistance. What that really means is that the bigger the resistor, the bigger its share of the voltage drop. It's that simple, predictable division that makes the circuit so incredibly useful. Okay, theory is great, but let's make this real. Here's an example. We've got a 16-volt source and this chain of 4 resistors. Our mission is to figure out V3. That's the voltage specifically across that 300-ohm resistor. Out of the total 16 volts, how much of it ends up there? So we just take our formula and start plugging in the numbers. Our total source voltage is 16V. The specific resistor we care about is the 300-ohm one. And then on the bottom, we just need the total resistance. So we add them all up. 1,000 plus 200 plus 300 plus 100. And when you run the numbers, boom, exactly 3 volts. This is just a perfect illustration of the idea. We use the other resistors to sort of soak up the extra voltage, leaving exactly 3 volts for the component we care about. We took 16 volts and stepped it down to 3, just with a few simple resistors. Okay, so we've got a handle on dividing voltage. It's time for the second tool in our kit. What if you don't want to change the electrical pressure, but you need to split the actual flow, the current itself? Well, for that job, we need a current divider. Now look closely at this circuit. See the difference right away? Instead of being in one long line, our resistors are side by side. This is called a parallel connection. So now the current comes along from the source and it reaches a fork in the road. It has to choose. Which path is it going to take? And that leads us right to the definition. A current divider is just a circuit that takes a main current and splits it up into smaller currents that flow down different branches. It does this using resistors in parallel. You're basically giving the electricity multiple paths to follow, and you can control how much goes down each path. Now, here comes the formula. And you gotta pay attention here because it's a little weird, a little counterintuitive. To find the current in the first branch, I1, you take the total source current, IS, and multiply it by a ratio. But look, it's R2 divided by the total. The current in branch 1 actually depends on the resistance in branch 2. Just think of it like water. If one path is harder to get through, more resistance, more water is going to flow down the other, easier path. All right, let's put our new tool to the test. We're going to tackle a slightly trickier example now, just to see how this works when we have more than 2 paths for the current to split between. So here's our challenge. We have a total of 22 amps of current coming into this circuit. It hits a junction and splits 3 ways. Our job is to figure out exactly how much of that current, I1, decides to go down that first path through the 200-ohm resistor. Now, you might be thinking, wait a second. Our formula was for 2 resistors, but we've got 3 here. And you are absolutely right. So here's our game plan. First, we're going to cleverly combine the 300 and 100 ohm resistors into one single equivalent resistor. Then we can redraw the circuit, which makes it a much simpler two-path problem. And finally, we can use the formula we just learned.
And you can see that simplification right here. On the left, you've got the original problem with its 3 branches. And on the right, we've combined those 2 resistors into a single equivalent 75 ohm resistor. So now the problem is much easier to think about. How does our 22 amp split between a 200 ohm path and a 75 ohm path?
So now we can finally plug the numbers into our formula. We're looking for I1. We start with the total current, 22 amps. Then we multiply that by the resistance of the other branch, which is our new 75 ohm equivalent. And we divide all that by the total resistance of both branches, 200 plus 75. And the result is 6 amps. Perfect! Out of that total 22 amps flowing into the junction, we figured out that exactly 6 of them will choose to flow down that first path. We've successfully divided the current. So let's just step back for a second and look at what we've done. You have now officially added 2 incredibly powerful, incredibly fundamental tools to your electronics toolkit: the voltage divider and the current divider. They're kind of like the yin and yang of basic circuit control. This table just lays it all out perfectly. Let's run through it. Purpose: one reduces voltage pressure, the other splits current flow. How are the resistors set up? Series for voltage, parallel for current. What's the key principle? Voltage divides based on resistance, but current divides based on conductance. It takes the path of least resistance. And the use cases? Powering low voltage components versus sending the right amount of current to different parts of a circuit. So if you only remember a few things from all this, make it these. 1. Voltage dividers use resistors in series to drop voltage. 2. Current dividers use resistors in parallel to split current. These are not just some obscure rules. They are fundamental patterns you will see over and over again in electronics. And really, they're both just clever practical applications of Ohm's law. So what does all this really mean for you? It means you now have the foundational tools to actually control voltage and current in any project you dream up. You can take any power source and shape it, tailor it to exactly what your components need. This is a massive leap from just knowing the theory to actually being able to build things that work. And that leaves us with one last really exciting question. Now that you have the power to divide voltage and divide current, what are you going to build first?